Hello, everyone, and welcome back. Sorry if I sound a little funny in this week's videos. I'm a little hoarse this week. This week, we're going to be discussing linked lists. Linked lists are similar to arrays in that they hold sequences of data, but they are very different in memory. Imagine for a second a tray of beads where each bead represents data. If it's on a necklace, you can only access them in order, as opposed to in a tray where you can access them just by picking any one up. That's the difference between arrays and linked lists. We're looking at no longer having this randomized access to data. Let's jump in with some code. We're going to start by just looking at an example of an array, just to really get an understanding of what I mean by having this random access. So let's look at just for a second here at an array, int array bead tray, and it'll be equal to size 5. Actually, let's just give it immediate values, 10, 20, 30, 40, 50. There we go. That's supposed to be a 10, not that it really matters. And then let's just go ahead and print out the value that's stored in index 2. All right, let me get my terminal up and running. Oh, not in downloads. We're going to desktop. And of course, as we expect, not position 0, not position 1, but in position 2, we get 30. So just like we expected, we're actually able to access pretty much any position in here just by referencing out this value. What's actually happening under the Java hood, if you want to know, is, as we know, if I try to print out the entire array, I get this memory address. This memory address takes me basically to this whole array, and then using arithmetic, just math, if I say 0, 1, or 2, Java is able to determine which value in here I actually want to go to. It takes the memory address, it does some math, and it says move over 2 spots so that we can get all the way to tray at spot 2. So it goes over here and it grabs that value, and that's how we get 30. Now, we're able to do that because arrays are stored in continuous or contiguous memory blocks. This means memory blocks that are right beside each other. Each block is directly beside each other. This does, however, cause a problem if we want to try to insert a value here. As we know, if we try to insert a value here, we get a really big problem. Because we have this continuous memory, if there isn't space in here, we have to make a new array of a larger size, and then we can do our insert. If there does happen to be space here, as in an array that is only partially filled, we still have to shift all of these values over to make space for this new value in the middle spot. That can be a real pain, especially if we have a really long array, let's say. If you know you're going to be doing a lot of inserts and that they're going to be happening sort of in random spots throughout our list of values, maybe we want to try a different approach. And this is where linked lists come in. Linked lists flip this idea completely. Rather than having this tray of beads where they're all aligned very nicely, one after another, we don't have a tray at all. We just have a bunch of beads sort of randomly scattered, and we pick them all up and put them on our string. The only way that we can actually get access to them is by going through them one by one. Each bead knows its own data, and it's aware of the bead that is standing next to it. And that's all it knows. This involves us making some classes. A class node. Now, like I said, the node will hold, the data itself, although this should be private. And the node is also going to hold, now this is the part that gets confusing, a pointer to the next node. Imagine you were standing in a line of people and you weren't allowed to look at the person in front of you. You could only look at the people behind you. So you're all standing there, but like kind of backwards. You know your own name, and you can see the next person in line behind you. And that's the only information you have. So if you wanted to be able to find out your position in the line, You couldn't just look in front of you. You'd actually have to have the person at the front of the line go to the next one and start counting. It's kind of a weird example, but that's exactly what we're dealing with here. Let's add a constructor so that we can access this data nicely. This dot data will be data, and this dot next is going to be equal to next. We're also going to need some getters and some setters. Actually, for this example, we really won't. We'll just need maybe our toString. We'll still need a getter. We need a getter, but that's it. Public node get next. Return next. And our toString to actually print out our data. We'll just go ahead and write a quick toString here like this. This dot data is equal to, this dot data plus, actually that's it. We just need our data. When we print it out, we just want to know what's actually stored in there. All right, so how is it that this is going to work? Well, let's take a look. We're going to dive deeper into this in my next video and subsequent videos, but let's just start with first value. And it's going to be equal to a new node 10. And initially, if it's the only value that we have, it looks something like this. Now, because our beads are not in a neatly arranged way, our job is to link them up as we go. So for example, if we want to make the next value, we need to actually be able to say that the next node that we're connected to will be the first one. This is how we bridge those connections. And again, I'm going to go into deeper discussion around this in my next video. Second val. There we go. Now, right now, of course, we can see I'm making many node variables that are accessible individually because I have these variables, first val, second val, third val. But if we just want to imagine for a second a bit more what this might be like in the real world, it would look something like this. And if I want to print out my first value, that's not going to be a problem. I can print out the value 10. Data 10. But to get this 20 out becomes a little bit more confusing. There's no easy way. I cannot just say, go to the next element, or I guess in this case it would be here. If I want to get that next value out, I actually have to go and grab it using .getNext. And now I can access data at 20. We have a couple of different considerations when we're thinking about arrays and linked lists. Arrays are difficult to insert and delete into because we have to shift all the time when we are dealing with array values, thanks to that idea of contiguous memory. Linked lists, however, are really easy to insert and delete from. These ones just involve a swapping of those pointers. Swap pointers. No values actually have to move around in memory, making it way less expensive. When it comes to searching, we can do things like a binary search in arrays, as we've seen in previous videos. Because we have this random access to our data, random access, things like searching are really easy, or even getting by index, These things, such as searching and getting by index, are much more difficult in linked lists because the only way to do it is to pass through every single node on your way. You have to go node by node, one by one. There is no random access. So this becomes a lot more difficult. So when should we be using these? How do we know if we should be picking a linked list or an array? How do we know which one makes the more sense? Well, are we doing a lot of inserts? Because if we are, a linked list is going to be better. It's going to be a lot faster for us to be doing linked list inserts than it will ever be to do an array insert. Are we going to be doing a lot of searching? Well, it depends. Is it ordered searching? Oops, ordered. An array is always going to be better because a binary search is so fast that it makes the most sense for us to sort of eat the cost of the inserts so that we can have that quick ordered search. If it's unordered, it doesn't matter. You can use either because in either scenario, we do have to go one by one. What about if memory is an issue? Which one is going to be better? Well, an array technically takes less room if full. So if you know the size of your array that you need and you're able to fill it all, this takes up less room. But if you don't know the size of your array, this doesn't take up more. This doesn't work. Unknown size. An array may waste space. And a linked list, yes, has the extra pointer. Linked list, list has an extra pointer to track, but it's always the right size. So as we can see in our use cases, there are trade-offs between when we want to use a linked list versus an array. Linked lists give us this extra flexibility of how we're actually moving through our data, and they're actually the basis of a lot of data structures that you are going to see into the next year and years of your computer science education. So it's really important that we get a nice solid foundation now. As we move through the rest of these videos, we are going to talk about things like searching through them, inserting, deleting, updating, and maybe even take a sneak peek at some of the abstract data types that you may start to find very useful that we can really only do well with linked lists. I'll see you in the next video. Thanks, everyone.